wonder how you train a giant AI model without breaking the bank or your hardware? Let's rewind to DeepSeek-V3. It runs on just 2,048 GPUs. Yep, and still competes with the biggest models out there. How? The team got smart. They designed the model and the hardware to work together. They shrunk memory with something called multi-head latent attention. They used mixture of experts to make the model faster and cheaper. And they even added a trick to guess more than one word at a time to speed things up. It's like building a race car and the racetrack at the same time. Faster, smoother, and way more efficient. Let's dive in and see how they pulled it off.
Let's start with the big picture. Large language models, think GPT-4o, Claude 3.5, LMA3, have been getting bigger and smarter. But scaling them up isn't just about throwing more parameters at the problem. Hardware bottlenecks start to bite. Memory gets tight, computation gets inefficient, and connecting thousands of GPUs becomes a logistical nightmare. So what's this paper about? It's not just another deep dive into model architecture. Instead, it looks at how hardware and model design influence each other. What we call co-design. The goal? Make large-scale training cheaper and more practical. Take DeepSeek-V3, their case study. It was trained on just over 2,000 NVIDIA H800 GPUs, yet it competes with models from giants like Google or Meta that use tens of thousands of chips. How? By being smart about design. Techniques like multi-head latent attention, MLA, save memory. Mixture of experts, MOE, cuts compute costs, and FP8 precision squeezes more out of the hardware. They even used a fat tree network to keep cluster costs down. This isn't just about building a better model. It's about building a smarter system. Now let's dig into how they pulled this off. The paper lays out 3 key themes: how hardware shapes model design, how models push hardware forward, and what we can learn from DeepSeek-V3 for future systems. First up, memory efficiency. As models grow, memory, especially high bandwidth memory, HBM, can't keep up. One major pain point? The key value cache during inference, which blows up with long conversations. DeepSeek-V3 tackles this with MLA, compressing key value tensors into a shared latent vector. This slashes memory use without losing long-term context. They also explore other tricks, like sharing keys and values across heads, or using sliding window attention. But MLA stands out because it keeps memory lean while preserving performance. And when you're dealing with thousands of GPUs, every kilobyte saved adds up. Now let's look at the diagrams. Check out the architecture layout at the top. DeepSeek-V3 is a transformer at heart, but with some clever extras. See those MTP modules? They're like speculative execution in CPUs, predicting multiple tokens ahead to speed up generation. If the guesses are good, the model skips ahead, saving time. Next, zoom in on the MLA diagram. Normally, each attention head stores its own key value cache, which eats memory. MLA avoids this by projecting keys and values into a smaller latent space. Instead of storing all that raw data, you keep one compressed vector and unpack it when needed. Then there's DeepSeek MOE, their mixture of experts setup. Here's the idea. Not every token needs every parameter. A router sends each token to just a few experts, one shared, plus a couple of specialized ones. So even with hundreds of billions of parameters, only a fraction are active at once. It's like calling in just the doctors you need, not the whole hospital. And all of this is precision aware. Some parts run at FP8 for speed, others at BF16 or FP32 for stability. It's a careful balance, tuned for performance. Let's talk numbers. First, memory use. With MLA, DeepSeek-V3 caches just 70 kilobytes per token. Compare that to QWEN 2.5 at 328 kilobytes, or LMA-3.1 at over 500 kilobytes. That's a huge win when memory is tight. Now, compute costs. Look at Table 2. DeepSeek-V3 has 671 billion parameters, but only needs 250 gigaflops per token. LMA-3.1, 2,448 gigaflops, almost 10 times more. The secret? MOE. Only a subset of parameters activate per token, so compute stays lean even as the model grows. This pays off in real-world use. On a consumer GPU, DeepSeek-V3 can still hit 20 tokens per second, fast enough for local deployments. And in ideal conditions, with perfect overlap, they estimate a ceiling of 67 tokens per second. Of course, Real-world bottlenecks like network delays can slow things down, but it shows what's possible with careful optimization. Speaking of speed, what if we crank up the hardware? Imagine using NVIDIA's GB200 NVL72 with its 900 GB per second bandwidth. Communication time for expert parallel steps could drop to 6.7 microseconds, theoretically pushing 1,200 tokens per second. That's just a projection, but it shows how much headroom there is with better networking. Then there's multi-token prediction, MTP. Instead of waiting for one token to finish, the model guesses a few ahead and verifies them later. It's like predicting the next words in a sentence and fixing mistakes if needed. This speeds up generation, especially for large batches. For reasoning models like GPT-4 Turbo or DeepSeek-R1, smart scheduling is key. They overlap decoding and communication to keep GPUs busy and reduce idle time. And every acceleration trick, MLA, FP8, MTP, gets tested small-scale first, then fine-tuned. For example, FP8 fine-tuning drops accuracy by less than 0.25% compared to BF16, thanks to careful optimization. Now let's talk hardware upgrades. The paper suggests two big ones: higher accumulation precision, more bits during math ops to reduce errors, and native support for fine-grained quantization. This would let hardware do compact math in one go, cutting memory traffic. Then there's communication compression. DeepSeek-V3 uses log-FMT, a logarithmic floating point format. Instead of linear values, it stores numbers as base 10 logs, covering a huge range with fewer bits. Compared to standard 8-bit formats, log-FMT is more accurate and great for MOE training. Now, check out Figure 2, the H800 compute node layout. 8 GPUs, linked by NVLink switches, with each GPU also talking to a CPU via PCIe. This setup balances bandwidth constraints, especially since H800 NVLink is slower than the H100s. It's all about keeping data moving smoothly, both inside and outside the node. This sets the stage for how DeepSeek-V3 handles parallelism, which we'll dig into next. Parallelism is where things get spicy. First, they skip tensor parallelism during training. It's just not efficient with limited NVLink bandwidth. Instead, they use enhanced pipeline parallelism, called dual pipe. It overlaps attention and MOE computation with communication, keeping GPUs busy and cutting idle time. Then there's expert parallelism. With 8 400 gigabits per second InfiniBand NICs, they hit over 40 gigabytes per second in all-to-all expert routing. They even open-source their implementation, DeepEP. Here's a clever trick: node-limited routing. They split 256 experts into 8 groups, 32 per node. For each token, they route to a shared expert and a few routed ones. If experts are on the same node, great list traffic. If not, they prefer NVLink over InfiniBand to reduce inter-node hops. They even deduplicate traffic to avoid sending the same data twice. But there are limits. Intranode and internode bandwidth don't always match up. The solution? Unified communication protocols, dedicated coprocessors, and smarter routing hardware. Now let's talk network design. First, avoiding bottlenecks. If key-value cache data and expert packets fight for bandwidth, things slow down. The fix? Prioritize traffic in separate control and data lanes. They also suggest tighter hardware integration, like putting network cards right on the CPU's input-output die. This cuts latency by avoiding chip-to-chip hops. And linking GPUs to CPUs via NVLink, not just PCIe, helps too. Now, check out Figure 3, the multiplane fat tree. Imagine multiple independent highways for communication. Each GPU connects to a dedicated network plane, reducing cross-traffic and scaling to thousands of GPUs without congestion. Why is this better? It builds on existing NVIDIA tech, halves switch hops compared to a traditional fat tree, and isolates traffic so one busy plane doesn't slow the rest. It's like giving every GPU its own fast lane. How does this network hold up? Look at Figure 4. Each GPU's interface splits across multiple planes, spreading traffic evenly. Table 3 compares it to other topologies like Slimfly or Dragonfly. The multiplane fat tree scales to 16,000 plus GPUs, costs less than Dragonfly, and uses fewer switches than a full fat tree. Now, real-world tests. Figure 5 shows all-to-all communication, every GPU talking to every other GPU. Even as GPU counts scale, bandwidth stays strong. That means no performance hit for better fault isolation and scalability. They also measure training performance using MFU scores, floating point ops in attention layers. Across scenarios, the multiplane design matches conventional setups while adding robustness. And InfiniBand still beats Ethernet, ROS, for latency-critical tasks like weight syncing. Let's validate this further. Figure 6 compares latency between multiplane fat tree, MPFT, and multi-rail fat tree, MRFT. They're nearly identical, so MPFT adds no overhead. Now, Figure 7, expert parallel workloads. GPUs process thousands of tokens while doing all-to-all communication. Throughput nears the full 400 gigabits per second bandwidth, proving the system handles heavy traffic well. Table 4 shows training stats, tokens per day, step time, FLOPS, GPU utilization. MPFT and MRFT are neck and neck, so network design isn't the bottleneck. Table 5 digs into CPU latency. InfiniBand wins, especially in same-leaf and cross-leaf setups. Every microsecond counts in large-scale training. ROS, while cheaper, struggles with switch limits and inefficiencies. But with better routing policies, like adaptive paths or congestion-aware queuing, it might catch up. Now, broader hardware challenges. Figure 8 shows how routing strategies affect ROS-E bandwidth during collective ops like allgather. Adaptive routing wins, especially under load. Then there's IBGDA, a neat trick, letting GPUs bypass CPUs for RDMA work requests. This cuts latency for small packets, common in large-scale training. Reliability is huge. Failures come in two flavors: hard crashes, like GPU failures, and silent data corruption, memory faults or rounding errors. Silent errors are nasty. They can spread undetected. The fix? Checksum validation or hardware error detection. CPU bottlenecks also hurt, especially PCIe delays. The solution? Direct GPU-CPU links, like NVLink, or offloading CPU tasks to coprocessors. Bottom line. Scaling AI needs smarter networks, fault-tolerant, low latency, and adaptive. Finally, future directions. First, co-packaged optics, embedding optical interfaces in network chips for more bandwidth and less power. Then, lossless networking with credit-based flow control, but watch for stalls. Adaptive routing is key. Dynamic paths avoid congestion, crucial with thousands of GPUs. Fault tolerance is a must. Systems should self-heal without pausing training. In-network computation is promising. Offload tasks like aggregation to switches, freeing GPUs. And smarter memory semantics, like acquire/release fences, could cut sync overhead. Then there's the memory wall. 3D stacked DRAM and wafer-scale integration could break through, boosting access rates for the next AI leap. The takeaway? Scaling AI isn't just about bigger models. It's about smarter systems, from hardware to networks to memory. Thanks for joining us today. Happy exploring together!